Hey guys, today in this video I am going to show you a deep comparison or just a shallow comparison with Python 3, Python 2 and C and C++. So let's get started, right? Uh, so here as you can see that there are three programs. The one is prime.py, that's a Python code, then prime.cpp, that's the cpp code, then there is prime.c, that's the c code. I have compiled prime.c to prime underscore c and prime.cpp to prime underscore cpp, and prime.py was just compiled just for the sake of having this done in real quick, because Python is very slow and compiling might just boost it, or maybe not. The results were similar anyway. I think it did not boost it, but anyway, with all out of the way, let's get into the main test. So I'm going to compile these codes once again. So I'm going to remove prime underscore c, prime underscore cpp, and let me open the code. You can see the code and it will be in the description. All the links to the code and everything will be in the description. Yes. So let me compile. So gcc prime dot c minus o prime underscore c minus o, sorry, I type my speed minus o. So this should give me prime underscore c. If we run prime underscore c, it should lead all the prime numbers up to a thousand or something like that, 1 million. Anyway, with that out of the way, let's take a look at prime.cpp. Oh, I missed an R, didn't I? Prime.cpp. Here's a look at prime.cpp. Here we are using iostream instead of stdio, and also cout instead of printf. It's a bit similar, but anyway, since I know the code, I just used the I just converted the C code into C plus code. Anyway, let's compile that. So g plus plus prime dot cpp, oh shit, cpp, then output to prime underscore cpp, then we should get all this one. So let's run prime.cpp. Yeah, please, hunky dory. Okay, now take a look at prime.py. So as you can see, same logic has been applied here, and the code is smaller just because there is no curly brace and all. Anyway, the code will be in the description. So let's run prime.py. I'm not making it an executable because it will add lines of codes. So anyway, you can also, like, this was Python 3. If you're not sure, then I can, like, see, it's Python 3.6. So if I want, I can run the same code in Python 2 because I have specified parentheses in print statement, so it should run on both. So with that out of the way, how we are going to measure the time? That's a great question, but bash got us covered. There is a function called time in bash. It's not a command or anything like that. It's actually a shell feature, basically a bash feature. No other shell has it, or some other shells only have it. Anyway, if we use time, a command like sleep one, it should sleep for 1 second, right? Yeah, you can see that it slept for 1.002 seconds. That will be the time for reading the sleep that program from the disk and executing that, then finalizing everything. So that plus the sleep program sleeping for 1 second, so that makes it 1.002 seconds. So as I can see, the program ran for 1.002 seconds, but it was not doing anything with the system, or user was doing nothing with the CPU. So it was simply idle, and we can see that here. So with that out of the way, uh, let's get into the program. So after running time of Python prime dot py, you can see that the results are out, and the results are 5.455 seconds. Actually, I have copied all the results here. You can see that it's similar to that. It's like wiggling around in the 40s and 70s. It's between that. No PC is perfect, and so many processes and all, it unevenly loads the system. So the program execution time might wiggle just a little bit. Anyway, you can see the time taken. That is the real time taken, including the time for the program to load from the disk. We will be considering that. Or anyway, the results are here. You can consider anything. You can see that the program ran very slow, right? That is similar with Python 2. This is, I think, something error with that execution. So let's go to Python 2, right? Running it in Python 2, it's similar. Yes, this ran within 5.349 seconds. It is a little faster, I have to say, than Python 3. I don't know why that is, but Python 2, it must be slower than Python 3, because they have optimized Python 3 more than Python 2. But anyway, in our case, the Python 3 performed worse than Python 2. Now let's go with C, right? So let's time C. Push. So you can see that that code took around 200 seconds, and in my results, uh, that is basically the same. See the same result here. If you run it once more, you will get a different result. Each time you will get a different result. You get my point, right? So anyway, let's go ahead and compare it with Cpp code. you can see that it's also changing. Anyway, let's keep it this result. um, Now let's go to like the results, and you can see that it's also similar. If I run it once more, maybe I can get the same result which was in the text file. Is this in the text file? Yeah, anyway, leave it. You got the point, right? So, what is my opinion about this? Python is a very good program language and it's very easy to code. And there are so many projects going on in Python, mainly related to machine learning and stuff like that. But it is very slow, and each line of the code have to be compiled each time before execution, or that's what most of the people say. I don't know about that, but anyway, Python doesn't really contribute to any real system usage. Like you can't run a Python program without any Python compiler or something like that in a system. But you can run a C code after compilation in any of the systems. If it is compiled for x86, you can use any so sorry for interruption. um, I like to take this in one shot, but my dad interrupted. Anyway, where was I saying? Like yes. Those for C, it's compiled to mission code. That mission code that is it can be executed um, by the processor itself. So if you can like exclude any OS and everything, the code might run. That is not the code, the binary file might run. But Python, you can get the code, you can only get the code. If you compile also, it's like a pseudocode or something like that. It has both the code and also um some of the things are compiled, but everything is not compiled. You can see that if I open a compiled Python document, like in the py cache. So if I there is nothing here, so you can use that. So you can see that this is gibberish, but if we go to some extent, we can see that some of the things we recognize, like a range, print, module, prime.py, these are we recognize. So this is not pure machine code. But if we go ahead and like uh, print out or edit prime.cpp, sorry, prime underscore cpp, you can see that it's completely gibberish. So this is real machine code, and it can run in PC without any support of any of the other programs. Yes, there are some things like these, but you know, uh, C code is faster than CPP, and CPP is faster than Python 3. Sorry, Python 2, and Python 2 is faster than Python 3. So that's all for today's video. Stay tuned for more videos, and subscribe if you have not subscribed already. I have cool things coming on lately, but anyway, I don't know what to post in this channel, but like uh, I'm having like a issue with my hobby. Like I have too many hobbies, like electronics. I have hobbies with building stuff from scratch, and I have hobbies like hacking stuff. There's so many hobbies, but I have to know what you like the more from this channel. Anyway, comment in the comment section about what you want from this channel. I'll be watching the comments from this video very closely. Anyway, thanks for watching and bye.